So to play around with item response theories in lavaan, there are programs that are specifically geared for item response theory. And you'll get the same answers out. One of the reasons that, at least for me, the issue of running IRT in lavaan turned into a bit of a rabbit hole was the example data set that I have contains missing data. And I kept getting different chi-square values and different threshold estimates out of lavaan from Mplus. And after going around and around with people and with my code, I went back and I threw out all the missing data. I mean, I didn't know what the problem was, but I got the results to match when I have complete records. And it seems that short text on those adventures is that the default minimization approach that lavaan takes was prone to a local minimum. And overriding that seemed to overcome the problem, and at least for this particular data set, gives me the same answers as Mplus. The other thing that you need to know about lavaan, although it may be changing in the future, is lavaan only supports the probit link function. So you cannot do logits, and that's not a huge problem. I have talked a little bit about a former student's book that uses lavaan, Alexandre Beaujean, and he has a book called Latent Variable Modeling Using R. And he runs his, it only uses lavaan, and he runs his model in lavaan, uses the link function, and then multiplies it by 1.7 to get the logistic out. But that's not really the logit link function. He's just making the standard deviation of the probit function have the same standard deviation as a logit function. So I'm not sure how to go through this. This is not going to take a lot of time, so by all means feel free to stop me and ask questions along the way. I'll set my working directory to be where on my computer this is running. And I'm going to read in an Excel spreadsheet here using the read Excel function. I made two versions of the data set here, one for my no missing data set and one for just the raw data set that I was playing with. So for the purposes of demonstration, let's just read in the data. One of the small things about this particular function is I just read this in from SAS, and SAS treats the dot as a missing data value. If you don't go in and change those dots to NA, when the read Excel function reads in that data set, it's going to say, oh, you have a dot in there, this must be character. So you have to go in and slap its little hands and say, well, actually, no, each of these columns are in fact numeric. The other fix around that is to go in and change them to uppercase NA, all the dots that is. That'll also work as well. You won't need this command. So, I then view the data set. So to get into lavaan, we will call up that library. And to do just an item response theory model, I'm going to mention only the variables that I have in the data set, and then I'm going to subset my data set and create a data set of only the +5 data items. Oh, excuse me. And in order to read this in, by default, lavaan is going to expect these variables to be continuous, and so you need to change the type of that so that it is categorical. And that's done with this command. So for across all of the rows and for the columns with these labels, I'm going to apply this command to it, the lapply statement, and say these are ordered. So there's that. And I can then take a look at the summary data. And I think it's a fairly good idea to always go in and check that against your raw data set. So I've got 819 zeros and 412 ones, for example, at wave 0, and I've got 543 zeros and 688 ones at wave 8. So here's our code for setting up a lavaan model. So what I did to create this was I went into Onyx and I drew a diagram and labeled all of the loadings as L1 and just output that script so I didn't have to type. So this is saying I have a tau equivalent model and I have fixed the factor variance at the number 1. And the thing that's new here is this set of code that is talking about the thresholds. So this is our variable, and this T1 says that this is the first threshold. If I had more than 2 categories, I would have T2, T3, T4 as separate lines. And this is the name of that threshold, TH0 for threshold. I just made it up. And the fact that these are all different means that I'm estimating a separate threshold for each of the variables. If, for example, in a growth curve model, I was doing common thresholds or one threshold that's set equal across the variables, those would all have the same name. By default, lavaan is not going to give you anything beyond the estimates of the factor loadings and the estimates of the thresholds. So if you're looking at an item response theory model, we need to put in some code to make a new variable that will correspond to the difficulties. And this is the code to do that. Now, the equation that we had from the handout that I sent you all was that the difficulty is defined as the threshold divided by the commonly estimated loading. And I do have to point out, if you're going into other item response theory texts, or if you go into Alexander's chapter on categorical modeling, he has a lot more complicated formulae that are in there. And those will give you exactly the same results that I have here. What he is doing and what item response theory people are doing is they're also estimating parameters that are A and B that are part of the 2-parameter logistic function. And so it's a little more rigmarole. The equations look more complicated, but I kind of like simplicity, and these formulae work fine. They match the results out of Mplus. And similarly, if we have our discriminations, this is the formula. So it's my common loading divided by the square root of 1 minus that common loading squared. And
I have a question. This part, so you said some portion you took from Onyx, but this part is the part that you wrote the code yourself?
Yeah, let me highlight all the parts that I wrote myself. So this is what you would have to write.
Okay, thank you.
And this is the part, well, I realize it's not that many lines, but I'm trying to highlight the fact that be lazy. It's really quick just to draw the diagram, if you have a small model inside of Onyx, and save the script. Okay, well, we can now run that model. And then we can run this. So lavaan will take theta or delta parameterization. And this command, if you set it, will do listwise deletion. So, this doesn't apply to this data set because it's a data set that has no missing data in it. But if you wanted to run the data without missing this, that's a statement that you would include. And the ordered statement tells lavaan which of the manifest variables Sorry, momentary interruption from my parrot, who decides to throw a glass off the table. It'll tell the program which are your ordered categorical variables. And this little bit in here is the default. It will do WLSMV estimation. And this is the command Boyden, Fletcher, Goldfarb, Shano optimization that did a better job, or at least got me results that matched with went on an M+. So that's the little bit of newness here. This is the default tolerance for the minimization. So if we run that, it runs really quickly. And then we can take a look at our summary. And we want to take a look at our fit measures. We'd like the R-square for the model, and we also want to take a look at the standardized solution. So to take a moment and walk through that, this is the technical information. This is our free parameters. For some reason, lavaan keeps track of our quality constraints. This is the regular chi-square statistic. And I don't really think a person should even put that in printout, because the one you want to use is the robust chi-square statistic over here. Because you want to adjust for the fact that these are categorical variables. And down here, the baseline model is another word for the independence null. And then relative to this chi-square and this chi-square, we can calculate CFIs and TLIs and an RMSEA with a confidence interval on that. And downstairs, here's our standardized root mean square residual. It defaults to giving me robust standard errors. And downstairs, here are my unstandardized solutions, the standard error, the wall statistic, that's an approximate C-test, and the standardized, where all of the X's and all the Y's, everything in the model is standardized. And over here, this is the model where we standardize only the latent variables involved. We don't have intercepts in this model because it's a continuous model. We're writing the defaults. If we were doing a more complicated model where we had thresholds being the same across variables, it would be possible, just as in M+, to estimate some intercepts, but that's why you see zeros here. And then downstairs here, we see the threshold estimates. So from looking at this, this is a probit length function. So this is saying that the threshold associated with pre-college drinking is higher, meaning, if a person engages in drinking 5 or more drinks in a sitting, that's more indicative of a more pathological alcohol involvement, or certainly a higher level of alcohol involvement. Whereas at later ages, like wave 8, the second semester of their senior year, it's indicative, not that indicative of a high level of the latent variable. And analogously, I've got the same standardized and latent standardized versions of those coefficients. One thing that is a small point of difference between lavaan and M+ is lavaan does not go out and recalculate standard errors on the standardized solution. So you may have noticed in an M+ printout, and we can kind of go back and take a look at that, you will get a standardized solution and you will get a separate set of statistical significance tests of the standardized coefficients. And that's kind of a numeric issue and for larger models. Downstairs, here we have our variances. Well, we fixed the factor variance to 1 here. And then what is this thing? Well, that's the variance of that proportion of that variable that is not explained by the latent variable involved. So I can take, I'm sorry, that's the proportion that is explained. So 207 is equal to 0.891 squared, sorry, 1 minus 0.891 squared, and that's what you got going on there. Here are our scaling factors. These are the latent, this is the scaling factor, that delta that we were talking about in the last lecture. And downstairs is the R square for that model. That 0.793 is 0.891 squared. So for comparison purposes, I can come back to the same model that we had for the Rasch model. This chi-square matches, my unstandardized loadings match, my thresholds match, my scaling factors are there. Here's my discriminations and difficulties. We'll get to those in a minute. And here's my standardized solutions. These numbers all match. So the next thing we can do now is to take a look at our difficulties and discriminations, 0.479, and in terms of my difficulties here, 0.479 matches and plus, and the corresponding standardized versions. And then downstairs, I have the discriminations. And recall that when we're talking about a Rasch model, because it's a tau equivalent model, the discriminations are all considered to be the same. So that's a Rasch model in lavaan. And I'll keep the chat bar open over here in case anybody wants to jump into the question in the chat bar. Now, whenever you're programming in lavaan, it's always a good idea to use Tech 1, get a listing of what your free and fixed parameters are. In Mplus, we run that check by running Tech 1. In lavaan, we have the inspect command, so I can run that. And what it will do is tell me where my fixed and free parameters are. So here's my individual factor loadings. And these are the equality constraints that I've got going on. So, this is a fancy way of saying parameter 1 is 2 is equal to 1, 3 is equal to 1, and so forth. And here they all are. I have no thetas because these are ordered categorical variables. I have no freely estimated psi matrix of variances and covariances of latent because I fixed the variance to 1. I have no intercepts because it's a categorical variable and I'm writing the defaults. I have no latent variable mean that's estimated because it's assumed to be 0. And down here are my thresholds numbered 10 through 18. I do not have any freely estimated deltas, scaling parameters, because I wrote the defaults there. Those are all the number 1. I have a feeling in the back of my head that I said all that quickly. Are there questions about it? And so if you're checking what you're doing and you want to know where the fixed and free parameters are, that's the inspect command is your friend. Okay, so our next thing that we can do is to consider the 2-parameter model. Well, that's going to be the same as the Rasch model, except now I'm going to freely estimate different factor loadings for all of my manifest categorical variables. And the code down here is the same as before. I'm going to name all these thresholds different things. And the difficulties that I want to calculate now will be unique and specific to that particular item. So the difficulty is going to be the threshold for the wave 0 assessment divided by the loading for the wave 0 assessment. But the next difficulty is going to use the loading from the first wave and the threshold from the first wave. And similarly, all of my discriminations will now be specific to the item, and I'll be using the loading for that wave to calculate the discriminations. So I can run that, and I can take a look at that output. It's the same as before, and I can look at the summary. And, here's my statistics and my baseline, and my fits. The fits are a lot better than the Rasch model. Here's my RMSEA with its confidence interval. It's still well above 0.05. And here's my SRMR. And down here are my different loadings that show that the factor loading for wave 3 or wave 4 seems to be higher than the factor loading for wave 0, for example. All right. And as before, I have no intercepts because they're ordered categorical and I'm writing the defaults. And as before, here I have thresholds. Now the thresholds are all different. Here's my variances. That is the variance that the variable, the latent response variable that's left over after taking out the variance due to the factor. And here are my scaling factors, and they're all fixed at 1. And here's the R square, which is the square of the loading. And here's my difficulties. And here's my discriminations. Any questions on that? So, so if we're coming back and looking at that in terms of the 2-parameter model. We have all of the same information as before. These chi-squares match, these loadings match, and our discriminations and difficulties match. It occurs to me that, it's also helpful to talk just a little bit more about the language of item response theory. We talked about the fact that we can get item characteristic curves, and we can just pull a few of these off. For purposes of looking at them. And you can see this item characteristic curve looks a little bit different across the items that I chose. You can think about an item characteristic curve as a cumulative response function. So it's the probability of answering the item correctly or of scoring a 1 given where you are on the latent variable. As I talk about in the book, another distribution you can look at is the probability density function. So if you're looking at a normal distribution, this kind of a curve in a probit length function, this would be a cumulative distribution function. And the probability density function is just the shape of the distribution that would happen. And that's called an information curve in item response theory. So if we were to come back and take a look at those, we can pull off a few items as well. And this is now telling you what part of the distribution a given item is telling you about. So wave 8, for example, is telling you about, is most informative about this range of the latent variable of alcohol use. And the wave 0 distribution is telling you about or providing some discrimination information about values that are above the average or above 0 on the latent response variable. And that's information, so to speak, about how each individual item in your survey is performing. We can come back and take a look at information curves taken across all of our items. That's In this particular case, that's going to look an awful lot like a normal distribution, but we can look at it. And there it is, that if I take all of the items in my little survey together, this is the part of the latent variable that we're informed about. I can take a little subset of that and say, well, what if I made an instrument that was based only on, say, items 5, 6, 7, and 8. That is the items that discriminated at the lower end of things. And you'll see that, this distribution moves a little bit. It's below the average of 0 here. So that's if you're playing around with doing diagnosis or trying to identify what subset of items are telling you about where on the latent distribution you're at, those partial functions can be useful to you. Any other questions about that? And that's basically all there is to lavaan. The other thing that occurred to me, given that it is November, is that it's helpful to take a look at the resources that you have. So as I mentioned at several points, the Google group that I have for this class, I keep open, and you can continue to subscribe to that. There's an awful lot of nice resources out there that can also be assistance for you. Let me come back into that. I've sent you in a separate message to the class these links. James Grice has a nice little website, and he's got a lavaan tutorial that's kind of useful. He summarizes lavaan code in a nice little PDF. And I like it because it's very brief, and it walks us through the syntax in a very little amount of time. That might be something you'd like to take a look at. And he's also got a nice section on Amos, if that's what you'd like to play with. There's a lot of multi-group examples that he goes through. I mean, I like James' work. Basically, he's still using older Bayesian estimation code called bugs. I would say probably maybe you'd want to go to the lavaan group and play around with lavaan as being an easier way to play with Bayesian if you decide to do adventures in that. The second thing is there is a Google group out there called lavaan, and you can post your questions, as you can see here, about your problems with lavaan, and they're very helpful. I've used that on occasion. And also there is a YouTube channel for Mplus, and this has really kind of exploded. I haven't been able to keep up with it nearly as much, but Banked goes on workshops across the country, Johns Hopkins, UCLA, and so forth. And he's posted those videos there. So if watching a video and watching someone talk about their code and how to think about it is your way to go about things, you can certainly find that. He does a nice presentation on how to do Bayesian analysis. And if you're interested, in my advanced SEM class, I talk about intensive longitudinal data and time series. And Mplus has a lot of new and exciting options in that you can get into. Intensive longitudinal data is a little bit different, in terms of its emphasis on Bayesian work than DSEM, which is a frequentist analog of intensive. So you can also take a look at those as well. And so those are kind of resources you can take a look at. There's a, I'm kind of move this down to where it is. This gentleman, I don't know personally, but he has an awful lot of webinars using SPSS and Amos. And if that's your platform that you like, it seems to be a fairly nice presentation. I mean, he seems to have some things going out there. So influence diagnostics, for example, for SEM. So I hate to say it today, but that's, you know, my prepared remarks for you. If you don't have, you know, comments about this material, I can talk to you a little bit more about some of the issues in equivalent models. Would that be what you'd like to see? Well, I'll charge ahead and do that. And because it's easiest to draw diagrams quickly in Amos, let's bring up Amos. So allow me to talk about a topic that is not talked about a lot in discussions of structural equation modeling, but it's important in the generation and evaluation of competing models. So consider for the moment a factor model, and let me rotate that around, and let me make it a little bit bigger. Now, you can fit this model. So I've got 5 indicators going on, and you'll get a chi-square out. The problem is that there's more than one diagram with causal indicators here that will fit this just as well in terms of chi-square. So on any data set, you can run a single factor model and observe the chi-square, but you're also going to get exactly the same chi-square if you also take one of your variables and move it over here and draw an arrow from this to that, and then add an error variance onto that. So this is an example of the equivalence question in structural equation modeling. And this happens, in psychology quite a bit, that people don't necessarily think about the fact that these two models will have the same chi-square, and they start to provide all kinds of conceptual interpretations about this competing model. I've reviewed, I think it was last year, a paper where they got different chi-squares doing this, and that's a problem. In other words, that the only way that the chi-square of the first model I showed you and this model is if one of those solutions fell into a local minimum. So more generally, when you're looking at a structural equation model, you have to think of a block of variables in which all of the variables are sharing a common cause or a common correlated error structure. And you can get an equivalent chi-square from a model by flipping only one arrow. If I flip 2 arrows, so if I did something like this, and fit this model, the fit of that model is going to be different than a single factor model. It's you can kind of tell yourself some stories why that might be the case, because over here, these two variables, the variances and the covariance of these variables will be perfectly replicated. And whereas in a one-factor model, they're not. So whenever you're looking at a latent variable, in one convenient little way to think about how this could mess up your data is, if you flip one arrow, is that going to change the interpretation of what you think your model is? Now, in a larger model where there is a block of variables to the left of this or a block of variables to the right of this, you have to be a little bit careful that all of the predictors of all the things that are predictors of this block of variables that we're looking at now have remained the same across the blocks. But that's, an issue for your reflection as you're trying to think about what your models mean. And that's, I can talk more formally about equivalent models if you like. So for example, if I had one predictor variable over here that was pointing at my latent variable, but not pointing at something else, flipping one model will result in a different chi-square. Perhaps as you're thinking about causal direction, one way to do an informal check on this is to play around with flipping it and observe if your chi-square model changes or not. All right. Well,
could you give us maybe like a practical example or a practical scenario of when we would do that?
I'm trying to think of his name. David Dubois used to be in our department, and he was looking at, I hate to, one of the frustrations I have in life is so much of the examples that I work with are psychopathology. And, the question there is, can I think of a set of items that will be representative of a latent variable? And okay, well, I can do just as we've talked about today, an item response theory model or a single factor, and I say, okay, here's my latent variable, and all of these manifest variables are but symptoms. And the conceptual game that David and I were talking about is, well, he said, you know what? I think maybe one of these items causes the latent variable and it's not caused by it. So for example, in the data set that we just looked at, you might say, well, what if pre-college drinking is the cause of college drinking? So I shouldn't be drawing my diagram as wave zero being caused by the trait of drinking, but instead that wave zero causes the level of alcohol consumption that I see in college. And in terms of the model, the chi-square of the model, the fits of those two models are identical. We do not have a basis for saying that structural equation modeling is going to tell us if one of these models is better than another. Well, that's kind of frustrating news, but it points to the fact that, from a philosophy of science standpoint, a given data set can be modeled, well by our theory, or it can be modeled poorly by our theory, or it can be uninformative. It can just not be able to judge based on our theory. So, the only way that you could resolve that issue of directionality is if you have a variable that is related to some of the data and not to others. And in the case of a structural equation model, there's a couple of ways to do that. You could say, instead of just observing data, I'm going to do an experiment. So we just kind of kill all this stuff and draw my model again. So if I had a data set And now at wave 0, I'm going to do an experiment and interfere in this data set. So let's say maybe my experiment will be, it's fun and I can run off at the mouse. So maybe the experiment will be, I'm going to randomly run around in dorm rooms and knock on the door and leave a 6-pack in front of their door. And in half of the people, I'm going to leave a 6-pack of root beer, and in the other half, I'm going to leave a 6-pack of actual beer. Well, and I'm then going to look at how that affects wave 0. So now I've got a treatment effect that applies only to wave 0. And it's not the case that alcohol can cause my manipulation because I assigned everybody at random. I knocked on random doors. So now I've got an indicator variable that affects one of the variables and not another. So if I start flipping this arrow, this is now going to be a different expression of what this single factor model is. But just doing an observation and looking at it, I don't have a solid basis for deciding the causal direction of any one arrow. But that's a great question, Joe. I don't know if I answered it, but that's also the reason why some people look at behavior genetic models, particularly if you can zoom into the human genome and find locations that are associated with particular behaviors that will allow you to tap into, are you looking at a genetic contribution that is associated with the trait, or are you looking at a genetic contribution, if you're really lucky, that zooms in on an onset age for psychopathology? That's another source of indicator variables that we can use to draw a better diagram. Is that helpful?
Helpful, thank you. Yeah.
All right.